Hello, everyone. Nice to see you here, and welcome to the second talk here in Castle House. I'll talk a bit on ElasticSearch and Docker and how to run those two together to make use of them. A brief introduction, I'm an engineer in Sematex Group. I do trainings, I'm a consultant, basically a person who goes all around the stack of our business, and today we'll get on with three things. First of all, Docker, then ElasticSearch, and finally a few metrics at the end that you should pay attention to whenever running ElasticSearch on a traditional bare metal, on VM, or in Docker, especially those were chosen for containers. So first of all, a few things about what we are used to right now. So every one of us developers are used to the development environment. When we do code, we test the stuff initially. Then we get on with the test environment where people test stuff together, right? So we have parts of the application coming from multiple developers that are connected together and test on some kind of test environment. Some larger organizations may allow and actually allow and do use quality assurance teams and QA environments where those are closer to production but still not there, and people do test. If something fails, they get back to the test and development, and the cycle goes on until we actually end up in the production environment where all those things run for our clients or for us, depending on what the applications are. The problems that come with it is there is at least three of them, the main ones. First of all, the resources are not utilized in a 80 or 90 or 100% way. So that means that we are more or less losing money because if we over-provision our servers, like here, we have some kind of processing power that we do not use, and we do not want that. Of course, some overhead is needed always, right? Because we need to be prepared for those spikes in usage and all of that. However, still, the over-provisioning is usually money that we lose. And the third thing that we can talk about here is that those environments are usually not the same. There are differences in the operating systems, the libraries that they run, the hardware itself. So there are problems. I suppose you all heard it works for me. And the thing, this is a problematic way, a problematic thing for developers to actually go there, look, okay, this is a library problem, let's fix that, let's update and go on with development. So instead of running in a traditional bare metal or virtual machines, we can put, in our case, ElasticSearch in a container, a small, lightweight piece of software, and put it on all of those environments in the same way, with the same libraries, and being sure that all of that will be run in the same manner. But the question is, why Docker? Three things that I could think of is, it's lightweight, it's based on open standards, and it's secure. So more or less everything we need for running successful applications, right? But why Docker again? If we will look at the traditional virtual machine and how that's run, we have a hardware layer at the bottom. Then we have a host operating system that runs that hardware. That's something that we need. On top of that, we have a hypervisor process that controls the virtual machine and allows it to run guest operating systems, those operating systems that are a part of each virtual machine. This is the overhead of a virtual machine itself because it needs a separate operating system. On top of that, we have libraries for the application, and finally, the application itself. This is how the traditional virtual machine stack looks like. Then we have the container stack that at the bottom looks very similar. We have a hardware layer and a host operating system. We can't get rid of that yet. Then we have more or less a hypervisor process. In our case, it will be a Docker engine that controls the containers and allows them to actually run. Finally, without the guest operating system, we have a small, lightweight container that instead of having the full operating system, provides us only with the needed parts and allow us to quickly and easily deploy and run application with its libraries without any issues at all. So as you can see, we remove the guest operating system from the equation, and we gain some resources needed for running that part of the stack. Why ElasticSearch? Distributed by design, based on Lucene, with great features, lots of features, search, aggregation, monitoring APIs, all the APIs that allow you to control and work with the clusters themselves. Of course, we talk to it with JSON, it responds with JSON, and it has a REST API that's easily usable for us. So now, how to run ElasticSearch on Docker? And again, this is a very straightforward process. We just type docker run -d and specify the name of the container, which in our case is the official ElasticSearch container, and things start. We can also run things like, say, latest, or use the version that we are actually interested in, like 2.0 or anything like that, and things will start automatically for us. So Docker will download the needed container, either from the official repositories or from private hub, and will start the container itself. We can also provide names for the containers, so they are easier to operate. We can provide environment variables, like having ElasticSearch to use a certain heap, like here with -e switch, and providing the proper environment variable understood by ElasticSearch, or provide some additional properties, like here -d node name, bbuzz, which will make ElasticSearch container use the node name and start a name with a given node. That's the basics of running. However, when you run multiple containers on a single bare metal machine, because we usually want to do that, because we want to maximize the usage of our hardware, not to lose money, we want to put some constraints on the containers so they are not using all of the resources that are available on the machine. Imagine that one of your containers run into GC issues or memory or I/O issues or anything like that. Then it can eat up memory, it can eat up CPUs, and we don't want to do that. We don't want it to do that. So we can, for example, put constraints on the usage of the memory, like with -m switch and specify 2G, which means container only use 2 gigabytes of memory at most. We can disable swap. By the way, all those constraints and commands are available in the reference documentation of Docker engine, so the link is in the bottom, so you can look it up. Those are only examples. In addition to that, we have the availability of specifying which cores of CPU we want to run with the container, so we can only limit some. If we have 24-core CPU like Xeon Intel processors, we can just say, okay, that container will use processor CPUs enumerated 1 and 3, and that's all, nothing else. In addition to that, we can also put quota on the CPU, further limiting down the number of cycles the container is actually able to use. The good practices around that is we should limit container memory, because we don't want it to use all of that, all of the memories, the large amount of memories we have in our bare metal machines. We should account for the I/O cache. That's especially true for ElasticSearch. We should limit the amount of CPU cores, remembering about the garbage collector. Because if we don't remember about garbage collector and we only constrain on some amount of cores for the container, we may end up with container not being able to run properly because GC will start to give issues. Of course, we can provide things like properties to ElasticSearch when running it in the Docker container, but we can also create our own images that are optimized for our use cases, right? So, for example, here we create a Docker file, a file, really a text file called Docker file, and we specify its contents. Here it is a very, very simple example of how you create an image, actually. So, from ElasticSearch means that it is from the official ElasticSearch container, and we will add a local file called ElasticSearch YAML and put it in the configuration directory of the container. Then a simple build command will give us the ability to build the container and run it without further modifying that. Those were two things, so configuration and constraints. Then we have to deal with memory. By default, the container doesn't expose any network outside of it running. So whenever you run ElasticSearch on Docker and you try to, for example, go to localhost 9200, you won't be able to connect to that container. And that's where port forwarding for Docker gets into play. With -p, we can tell which ports from the container should be exposed outside of the container itself. Here, we expose to ports 9200 for HTTP connectivity and 9300 for transport client connectivity to Elasticsearch. Now we'll be able to use the container outside of its own network in Docker. In addition to that, we can link containers together to create a very simple cluster, for example, on a local machine. To do that, we use the -- link, and we provide the name of the container that we want the starting container to link to. So here we link the container that we'll just run, we'll try to run to the container called ES1. And we specify the Xen unicast hosts for the container to actually know which Elasticsearch node to connect to. Here it would connect to the ES1, meaning that they would actually create a cluster in addition to when starting. And when the discovery kicks in Elasticsearch. Whenever creating your own containers, remember to add two things. First, the network publish host, and then the standard discovery Xen ping unicast host to be able to actually connect multiple containers to each other. Next thing, the good practices is about actually configuring a network to separate part of it for Elasticsearch cluster. Use the common names for Docker and common host names so that you actually know when you are looking at the containers what's happening there. Expose only needed ports, so don't expose anything unless you need it. This is good for security reasons. And finally, to have a good cluster and point the data and client nodes only to the master nodes so they connect to each other. They don't need to see anything apart from that. Of course, they will talk to each other internally, but whenever starting up and when the discovery needs to actually run, you need to only point the data and client nodes to the masters. Finally, dealing with storage. By default, the data in your container will be stored in user share Elasticsearch data. However, the problem that comes with it is that it is not persistent. So whenever container goes down or you kill it, the data will go away. There are two things we can do. First of all, we can map the directories from the container to our local disks. Like here, we map the user share Elasticsearch data to opt Elasticsearch data on our local bare metal machine, and it will stay that way, and the data will be there. Keep in mind permissions. You need to have properly set permissions for the inside process to be able to access the files on the disk of the host operating system. And the second thing is using the data-only Docker volumes, which are persisted and can be shared between containers. So they bypass the union file system, then can be shared between containers, as we just said, and the container can be deleted and the data will still be persisted in a state on a disk inside a separate volume container. So how to create them? It's as simple as running the following command: Docker create. We map some part of the our local disks to that user share Elasticsearch data. We provide it with a name it's needed, like here, ES data. This is the name of the container. And finally, when running Docker and the proper container, the Elasticsearch container itself, we can say volumes from and give that name that we've used so that the container running Elasticsearch will be using the volume container that we've just created. So this is about Docker itself, how to run highly available clusters with Elasticsearch. Remember about a few things. First of all, divide the roles of your nodes. So master nodes, there should be only master nodes, only data nodes, and only client nodes. So master nodes are not overloaded with the data and queries. In addition to that, remember about setting the minimum master nodes to 50% plus 1 master eligible nodes. That will help you with network splits and avoiding data corruption. How to run those? It's as simple as providing the proper parameters for the Elasticsearch container on Docker. We set node master equals true, node data equals false, and node the client equals false, and we have a running master. We do the same for the client, and we can do the same for the data node, just different place to set true. Of course, if we're running time-based data, which Elasticsearch is great for, we can also help each other, meaning we and Docker can help us to run the multiple tiers in our architecture. So usually you would end up with having hot and cold tiers, the hot tier for the recent data, real-time searches with all the indexing happening. And finally, the cold data, the archive for that. However, instead of creating different hardwares, instead of putting different hardware there, we can put different constraints on our containers and just say, hey, Elasticsearch -d node.tag equals hot. And then during index creation, we just use the standard routing allocation to put the index in a proper place. Now, if the container has more CPUs and more memory, it can handle real-time data while still have the same flexibility of moving containers around, starting them, stopping them on demand, and all of that. Of course, moving that data is also very easy as it's a part of Elasticsearch API. Finally, as I have 2 minutes left, I would like to tell you a few things around metrics that you should take care about whenever dealing with containerized Elasticsearch environment. So first of all, keep in mind that health API and shards API will give you the idea of the top-level view of the cluster. Monitor your CPU usage because that will help you knowing what's there in the container, how much stress you actually put on the container itself. If it's close to 100% in usage, that means that you don't have the overhead of spikes. That's bad because Elasticsearch and the cluster itself will crash whenever spikes happen, or you won't be able to use Elasticsearch because it will be overloaded. Keep in mind that the memory usage is also helpful for you, especially on the graphs, where you can see if you need more memory, more constraints, loosen up the constraints for Elasticsearch or not. In addition to that, I/O usage is again your friend because that will allow you to see, and especially with the correlation with merges and request rates, with what's happening there. If that's normal or maybe that spike there is about the merges and we have to do something about them, like loosen up and allow a longer tail of segments to be there for us to be properly running. Then the JVM heap and the garbage collection statistics allow us to see what's there in the memory of our JVMs and how the heap is actually being cleared up and how garbage collection works. Usually won't have fast, but often and very fast garbage collection instead of one but longer, which can lead up to the Stop the World GC event. Request and latency allows us to actually see how we are using our Elasticsearch, what's there, if the spikes there is something we know that will occur or something that happened, and we should take a look in that. If you are using 2.0 Elasticsearch and doc values, field data caches, mostly not an issue for you, but if you still do analyze or if you still use aggregation or analyze fields, keep in mind field data can kill you. Finally, indexing, again, something to look for because you will probably get a lot of indexing in your clusters, especially if you're doing analysis on time-based data. The last two ones, the refresh time, which will help you with seeing if you are actually okay with the refresh you have, or if it's too often, and how often it happens. And finally, the merge time, which will help you knowing how your I/O is used and all of that. So because we only have 20 minutes, if you have any questions to me, I would like you to get here. I'll be here standing and I answer them all. For now, that's all. Thank you very much for listening. I know it's been very short and fast, but we only have 20 minutes. By the way, if you're keen on that stuff, we are hiring at Sematex. Thank you and enjoy the rest of the conference.
Thanks, Rafał. We'll take one question, and then we have a short break before the next talk.
How do you supervise containers, and how do you handle container failures?
Actually, that depends on what you actually want to do. So how to handle container failures, right? ElasticSearch, along with the container itself, can be started without any issue. For example, if you have a monitoring software that will allow you to react on some kind of alert, like nodes going down, for example, a bare metal server went down, you can just spin up new containers. And the perfect thing around ElasticSearch that will be the data will be replicated without any issues. You can also use some kind of other more sophisticated solutions like Mesos and do all that spinning up and scaling automatically. So depending on what you actually want to use there, you have an options. For example, Mesos is a good thing to look at if you would like to have something that automatically reacts to what's being done with the containers. Right now, but that's a different topic. So yeah.
All right, let's thank the speaker again.
Okay, if you have any more questions, I'm here. Thank you.